So let's return to the statement of the nested intervals theorem. We will now proceed to prove it. Well, what do we need to do to prove this statement? First, we need to show that the intersection is itself a closed interval. And then we'll need to show that if the infimum of the distances goes to 0, that closed interval is in fact the singleton. For this proof, it will be useful for you to have a good understanding of what the supremum and the infimum of a set are. Because we have a sequence of nested intervals, we do have in particular that the interval in is contained in the first interval I1 for every n. So if I look at the set, which contains all of the lower bounds of the intervals, A1, A2, A3, A4, and so forth, that is bounded above by B1. If you're not sure why that would be the case, let's rewrite the inclusion here. What this is saying is that the interval AN, BN is contained in the interval A1, B1. In particular, anything in the interval AN, BN has to be smaller than B1. So, amongst other things, AN has to be smaller than B1. There's A1, B1, there's AN, BN, say. You don't have a choice. AN has to be to the left of B1. Otherwise, you will not have a sequence of nested intervals. Okay, so the set S is bounded above by B1. It is not empty. How do we know it's not empty? Well, it contains the lower ends of all of these intervals. And so, S being bounded above by B1 and not empty, it has a supremum. We'll call that supremum psi. Why is that the case? It's the case because R is complete. That's one of the properties of R that we've seen in the first section of this chapter. So psi is the smallest upper bound of the set S. In particular, what this means is that the lower end of all of the intervals, the ANs, are all smaller than psi. That's the definition of the supremum. Now we'll fix n. We pick a k, some integer. There's two possibilities here when we have a fixed n and we've picked a k. Either k is going to be greater than or equal to n, or it's going to be smaller strictly than n. If k is greater than or equal to n, then the interval in contains ik because we have a sequence of nested intervals. The intervals that come after are contained in the intervals that come before. And in particular, what this means is that the lower end of the kth interval is going to be smaller than the upper end of the kth interval. No surprise there. But also that this upper end of the kth interval will have to be smaller than the upper end, the nth interval. If I provide you with a drawing, you will see that this has to be the case. Here's AN. Here's Bn, here's Ak, here's Bk. That way Ik is contained in In. And sure enough, Ak is smaller than Bk, which is smaller than Bn, smaller than or equal to. If, on the other hand, k was smaller than n, then the inclusions here would be reversed. You would have to have that In contains Ik. That's because we're talking about a nested sequence of intervals. And you could play, roughly speaking, the same game to show that AK has to be smaller than AN. That's because IN is contained in AK, and that AN is smaller than or equal to BN. That's because we have an interval IN with a lower end AN and an upper end BN. In both cases, whether K is smaller than N or whether K is greater than or equal to N, AK is smaller than or equal to Bn. So what we get is the following inequality. Now what does that mean? Well, it means that this Bn for a fixed n is an upper bound of the set S. Bn is greater than any lower end AK, no matter what k you've picked. So Bn is an upper bound of S, but psi is the supremum of S. It is the smallest upper bound of S, and so psi has to be smaller than Bn. The n that we picked was completely arbitrary. We just picked one and fixed it. So this is going to be true for every n altogether. So on the one hand, we have that an is smaller than psi, something we showed here. On the other hand, we have that psi is smaller than bn for all n. So what this means, combined with the previous slide, that psi, the supremum of the set S, the supremum of all the low ends of the intervals, is contained between an and bn. Now you could play the exact same game, but instead of working with the set S of lower end of intervals, you would be working with a set T of upper ends of intervals, and this set would be bounded below by A1. Same sort of drawing here, curves. All of your BI's are going to be greater than A1. Now the set T is not empty, it contains all the BN's. And so what we have here is that the infimum of T exists. And in particular, you might be able to conclude that this infimum, let's call it eta, is actually smaller than or equal to Bn for every n. That's by definition of the infimum, the largest lower bound, the greatest lower bound. You have two options. Either k is greater than or equal to n, or it is smaller than n. If k is greater than or equal to n, In contains Ik, because it's a nested sequence of intervals. And in particular, while here we have a different set of inequalities that interests us, An is going to be smaller than Ak, which will be smaller than Bk, which will also be smaller than Bn, but that's not the part that's interesting to us here. We're talking about a different setup altogether. And if k is smaller than n, in that case In is contained in Ik again, because this is a nested sequence of intervals, and the inequality that we get out of this is that An is smaller than Bn, which is smaller than Bk. So it's still true that Ak is smaller than An, but we're interested in this one here. What we get is that pretty much no matter what, An is smaller than Bk in both instances. So what this means is that An is a lower bound of the set T, but we know that the infimum of T is eta, and so consequently eta is greater than An for every n. Eta is the greatest of the lower bounds. So if all of the Ans are lower bounds of T, they have to be smaller than eta. And in particular, what we get is that An smaller than or equal to eta, smaller than or equal to Bn for all n. Okay, so there's a lot of symmetry here, and I chose not to rewrite everything from scratch, just by highlighting the similarities between the statements. We're not done. In fact, we're nowhere near done. What else do we want to say? Well, we have that both psi and eta are within the interval In for every choice of n. This is what we found. But you know what else we have? We have that psi. We have that psi is a lower bound of T. How do we know that? If you go back a few slides, what we showed here. Psi is smaller than every upper end of interval Bn. It's smaller than all of the Bn, and so it's a lower bound of the set T, which consists of all of the upper end of intervals, all the Bn's. So being a lower bound of T, it has to be smaller than eta, because eta is the greatest of the lower bounds, the largest of the upper bounds. So psi has to be smaller than or equal to eta. You could also argue the other way, saying that psi is an upper bound of S, and so it had to be larger than psi, because psi is the smallest, the least of the upper bounds. Same argument. Either way, what this translates to is that An is smaller than psi for every n. That's one of the statements that we've proven. Psi is smaller than eta, according to what we've just shown here. Eta is smaller than Bn, one of the other statements that we've shown previously. And so the interval formed by psi and eta is completely contained in the interval in for every n. What this means, if it belongs to every interval in particular, it belongs to the intersection of the in's. We're not done. We wanted to show that the intersection of the in's was equal to a closed interval. And what we've shown here is that a closed interval lies in the intersection of the intervals in. What remains to be done? You still need to show the reverse inclusion. How do we show this? Well, we show that every member of this set here is also a member of the set on the right. Let gamma be some element of the intersection. That means in particular that gamma belongs to every interval in, so that in particular an smaller than gamma, smaller than bn for every n. So on the one hand, here we get gamma is an upper bound for S, because it is greater than all of the an's, and also that gamma is a lower bound for T, because it's smaller than all of the bn's. Remember that psi as the supremum of S is by definition smaller than everything in the set S. What we've shown here is that gamma is an upper bound for S, so it's greater than everything in S. Similarly, gamma is smaller than everything in T, right? Smaller than all the bn's, but the bn's are all going to be smaller than eta, the infimum of T. And this is true for every n. Finally, what this says is that gamma belongs to the interval psi eta. So what you've shown now is that everything in the intersection of these intervals is also contained in the interval psi eta because of the definition of psi and eta as the supremum of S and the infimum of T, respectively. And so in particular, these two conclusions are met. You have to have that the intersection of the intervals is equal to the interval psi eta, closed interval. We make an additional assumption for this second statement. We assume further that the infimum, the distance, the length of the intervals is 0. What does it mean? Well, by definition, if you pick a positive epsilon, no matter what the epsilon is, arbitrary, you will be able to find an integer k such that bk minus ak is smaller than epsilon, and bk minus ak is greater than or equal to 0. It has to be the case because we're talking about intervals, and bk is always greater than or equal to ak. If you couldn't do that, if you couldn't find an integer k for which that was the case, then that epsilon value that we had here, the positive number, would actually be a lower bound for this set, the set of lengths, and it would be a lower bound which would be greater than 0, which we assume to be the infimum, the greatest of the lower bounds. So it has to be the case that there's at least one integer k that satisfies this inequality. But we know, by definition of eta and psi, that bk has to be greater than or equal to eta. And we also know that ak has to be smaller than or equal to psi. We know this is true because we have shown here that bn is greater than eta and psi is greater than an for every integer n. In particular, it's going to be true for this specific integer k. And if you put these things together, you will get epsilon is greater than bk minus ak. Bk is greater than or equal to eta minus ak. Well, if ak is smaller than or equal to psi, what we know is that minus ak will be greater than or equal to minus psi. So minus ak will be greater than or equal to minus psi here, which by definition, is going to be greater than or equal to 0. What this really says, this is true for every k, but this part here isn't as important. It's still there, it's still true, but what we've concluded here is that epsilon is greater than n minus psi, greater or equal to 0. And the epsilon we picked at the top was completely arbitrary. It could have been any epsilon. The only way for this to hold, given that epsilon had to be positive, not completely arbitrary, it at least had to be positive. The only way for this to be true for every choice of epsilon is if eta minus psi is equal to 0. In particular, that means that eta is equal to psi. And this concludes the proof. It will be very important for you to make sure you understand the proof. It's not an earth-shattering result. We will use the result, mind you. We will use it, but it's not that impressive. What we think is important for you to understand is the principle of the proof. How we managed to prove the statement. What it is that we had to do, how we decompose the proof in various pieces so that we could do whatever it is that we had to do. So if you're not fully sure what happened on your first pass, on first watching the video, watch it again. At some point, you should try recreating this proof from memory. Not because I think it's important to learn proofs by heart, but it's important to learn the prosody of a proof. Prosody is a word that talks about the songs we sing when we speak. English prosody is much different from French prosody, which is itself much different from Mandarin prosody or any other languages. You need to learn the rhythms of mathematical proofs. So this is one example. We will see plenty more.